Thank you so much. So I'll try and explain what I think about yielding in colloidal gels. I was a little too ambitious to call this topological origins of yielding in generally soft glassy materials, but really what I mean is where do colloidal gels yield from? And to explain that, I would need to first explain what I think the rigidity in colloidal gels comes from, or what are the minimal structural units that I can use to recover elasticity of colloidal gels from. So that's the idea. A little bit of, and so with the last question, I think this by itself is a topic we could discuss. What are gels and why gels? To me, they're examples of these space-spanning networks that are interesting from different applications perspective, but really what I consider a gel is this idea of a system-spanning percolated network of bonded components, and that can be physical or chemical. I'm more interested in the physical gels. To me, these are the distinctions. So in the chemical gels, usually these bonds are irreversible, and so the network that forms is more permanent. With physical gels, these are usually reversible, and so the network that you form is more dynamic and lively. And that has implications, for example, in terms of their mechanics. Usually one fails in a brittle manner, and the other one yields as a result of microplastic events. So I'm more interested in this type of gel, physical gels, where particles form these networks, and then they yield in a very dynamical way. I'm trying to understand that from a purely topological perspective, and I'll tell you what I mean. So again, I will need to take a step back and say, where does elasticity come from in these type of systems? There are a lot of work in that area, and I don't know if, for example, Stefano will talk about this later during the conference, but the general mean field view of this is, I was hoping this would work, but it doesn't. Anyway, is that you have this space-spanning network of particles forming these reversible bonds. There is a correlation length. There is a cluster length scale, or blob length scale psi. And if you know the properties of that, for example, what is the spring constant that links each of these bonds, each of these particles together, what is the structural morphology of the backbone within this cluster, and its size, you could, through some mean field approximation, recover the elasticity of each blob, and then expand that to describe the elasticity of the overall gel. This is the work that she and then basically Cantor and Webman theory did 40 years ago. And so that's an old understanding of this, which works for a lot of these systems for a certain volume fraction of solids. More recent work using graph theory by Jim Swan and Eric First, based on a theory that actually Emmanuel and Alessio Zaccone worked a number of years ago, basically uses graph theory to chop up networks of these particulate systems into those cluster length scales, those blob length scales, and through Cauchy-Born description, based on how many connections exist between each cluster and another cluster, explain basically or recover G prime as a function of attraction between individual components. So if I look at, for example, attraction strength of 6 kT between individual particles all the way to 16 kT, as a result of these are all depletion gels, not an experimentalist, so I don't understand the experiments at all, but what I think the main system was PMMA particles and non-absorbing depletion polymers, resulting in these type of interactions roughly. These are only central forces, so no bending potential between the particles. And so you can describe this elasticity of the overall macroscopic gel based on this Cauchy-Born mechanism. There is a very recent work by Emmanuel's group on this hierarchical nature of soft particle gels, talking about the fact that within the structure of these particulate gels, there is a hierarchy of length scales that involved, which comes from these individual components all the way to different cluster sizes that are resulting from those structures. And what is key, and I quoted from the paper, is, I'll explain in a second, and Emmanuel has promised to correct me if I'm wrong on that. So you can see this picture. These red guys are what they call singly connected bonds, where basically within the structure of the network, what are the components that are only connected through one bond? So if I basically break this bond, I've broken the network within that cluster. What turns out to be the case is that the geometrical arrangement of these singly connected bonds is the key to explain the fractal models that at the macroscopic level recover the viscoelasticity of these gels. And you can see that in a fractional model or in a ladder model, which basically brings out those hierarchy of length scales. So all of these to now get to, yes?
Are you sort of thinking more about tensile stresses?
So these are, I believe these are so these are simple linear viscoelastic moduli of the system. So you're looking at G prime, G double prime in simple, small amplitude oscillatory shear simulations. Yes, so these are all shear. And so at different volume fractions, and I believe at different attraction and strengths, so you're basically varying all the state variables within the system and forming these universal diagrams for G prime and G double prime. And they're all recovered through this fractional model with a single exponent, with the fractional model or the ladder model with many, many, many components. So what I'm going to try and do is try to understand a bunch of questions. So these are experimental results that Lilian Xiao, who's at North Carolina State, provides for us. And so these are PMMA particles as well, very similar to what you saw in that previous slide. So when I saw these, there were a number of questions that I was personally interested in, and I'm going to try and answer these questions. One is, a lot of those old models are built on this idea that there is a dominant length scale for the clusters. Obviously, that's not what you see in these ladder models, for example. There are multiple length scales involved in describing the structure or morphology of these gels. So is there, when you see this structure looking like this, do you see a single blob size? That's the first question. If not, what does the mesoscale structure look like? So if I look at the morphology, coarse grained into clusters, what do they look like? Okay, so that's the second question. If I understand this mesoscale structure or the cluster sizes or the distribution, can I recover anything about elasticity or gelation itself from that picture? And then the last question, which is the title of this talk, is now imagine you have this structure, you're going to put it under the formation. Where does it yield from? Okay, so that's another question. And to me, they're all interconnected. So what we do is we do simulations. These are dissipative particle dynamics simulations. Honestly, it doesn't really matter what you do in terms of the model, the specific choice of the model. What you get is, as you change the attraction and strength between the individual components, you get a gel. These are all at 20% volume fraction of solid. Again, only central forces, no bending potential involved. And
What is the range of the potential?
So this one is particle radius divided by 10. So 10% of the particle size. So this is what I call a relatively weak gel. It still is not really weak, 6 kT, all the way to really, really strong attraction between the particles. And the thing is, if I look at the G prime or elasticity of these networks from those experiments that I showed you, they range, and these are really weak gels, right? So these are below 1 Pascal. But they scale like this as you increase U over KT or attraction between the particles. So we want to see if we can recover any sort of similar increase in elasticity as you change the attraction between the particles. So the very local measure of a structure that a lot of people use is coordination number, or how many particle contacts each particle has. So this is contact number and its distribution as a function of attraction strength. And what you can see is that that doesn't change much. So the overall local structure of the particles doesn't really change much and doesn't tell me much about why the overall elasticity is changing that dramatically. So this is just a comparison between the simulation and experiments to show you that we are roughly modeling the right system. So these are at similar attraction strengths and volume fractions. So we are gonna basically, because we need particle positions at all points, we're gonna focus on our simulations. So what we use to dissect our network into its mesoscale structures is what we call Gaussian mixture model. It's a well-established method that is used in network science. The way it works is, I'm not gonna go too much into details of this. If you have questions, I will try. But the general idea is there is an iterative process where you say, imagine you have 1,000 particles within one network, right? You start by saying all 1,000 particles belong to a single cluster. And then you say, I have 2 clusters, 3 clusters, all the way to 1,000 clusters, right? Well, basically each particle is one cluster. And there is a responsibility of cluster K to each point, each node within the network X value to be calculated. And from that, there is a log likelihood function for expectation maximization that you calculate. And then through that, there is a Bayesian information criterion that tells you exactly, through that iterative process, how many clusters do you have and which node belongs to what cluster. So it
explanation that I understand.
So if I have one cluster and 1,000 particles, everything belongs to that one cluster. Okay, so that's one condition. I can fill these equations that you don't have to really care about details of. But the second step is I have 2 clusters and 1,000 particles. What are the chances of this particle X belonging to cluster 1 or cluster 2? Particle 2, cluster 1, cluster 2. Particle 3, all the way to total number of particles. So you calculate that, again, through this probability function. So it's a mathematical expression that tells you what are the chances of this particle belonging to a cluster. And these are all happening in latent space based on who's connected to what. So I know the connections between the particles. So if I belong to a cluster, what are the chances of you who are connected to me belonging to the same cluster?
What order are you going?
So you do this for all conditions possible. So it's almost like an entropy calculation. So you're considering all the micro configurations.
Some kind of Renyi entropy, Q log Q, or Q to the power something log something.
No, it is an approximation to the Bayesian marginal likelihood.
Okay.
Exactly. So I'm not sure if I'm understanding the question.
There are other kinds of entropy. That's all.
Okay.
I think it's kind of related. So the step before that, to define a cluster, so what's the criteria for that?
Oh, the only assumption we have is that the distribution of degrees, which is the connections between the components within a cluster, has to follow a Gaussian. So that's where the Gaussian mixture model comes in. Basically, the idea is that the overall degree distribution within the network is a Gaussian, which is the case for the overall network. So the assumption is each of the clusters is also following a Gaussian. That overall, altogether, will give me the Gaussian for the entire system. So when I add them all together, I will recover the overall Gaussian for the system. So basically, there is no adjusting parameter. So this iterative process gives you an absolute minimum in that Bayesian information criteria, and so we just follow that. And so the result of that is this type of clusters that you get. I'm just visualizing parts of it, so you're not seeing the entire network. Everything does belong to a single network at the end, so remember that. We are just recovering communities or clusters within that one giant network. And now I'm visualizing those randomly to just give you an idea. So this is for the weakest gel we study, and this is for the strongest gel. And then, now that I have these clusters and their distribution, I'm trying to understand what they look like, what are the statistics of them, what are the characteristics. So, yes.
I mean, you're imposing certain conditions of the degree distribution.
Yes.
But what sort of gives you the guarantee that the network that you have satisfies that assumption?
There is no guarantee that it does, right? And so it doesn't, there is no guarantee, right? So basically you do this process and you find basically the most optimized version that is closest to that general degree distribution. But there is no guarantee that it's exactly what you're looking for, absolutely. So now that I have these clusters, and so one point about that is there are different ways in network community people use for community detection or cluster identification. And we have done a few of those. This is our choice, but what I can tell you is that statistically, when you choose, for example, based on clustering coefficient, you won't end up with a very, very different description. It's very similar to this. So what happens is, for example, now I can identify how many nodes belong to a certain, to each cluster and how big those are. So this would be cluster mass, the number of particles within each cluster. So there is a distribution. You have a small clusters, and then you have clusters that have 40, 50 nodes within them. So that's what I call mass. And there is a diameter, the physical diameter of the most farthest points within a cluster. So what you'll see is that maybe these are not clear, but if I plot one as a function of another, you'll see that if, for example, if I draw a horizontal line, that tells me at a constant number of particles per cluster, which cluster is longer. And it turns out it's always the stronger networks have more elongated or larger cluster physically. So I have the same number of nodes within a cluster, and that cluster, if the bonds are stronger, ends up being longer. So overall, stronger attraction, more elongated clusters. That's one thing. Yes?
Some kind of fractal dimension of those clusters?
You can, we have, but honestly, these are not really fractal objects.
What is the overall packing fraction?
These are 20% volume fraction overall, and these are depletion gels, so it's really not a fractal nature. But you can identify something based on radius of gyration and how many particles you have, a fractal dimension, and we have that. And it follows what you would expect. It's nothing surprising. But again, it's a very loose definition there.
It's only 40 or so particles.
Right.
So
I mean, what can you define?
it would not be a very meaningful quantity.
Yeah. So the next is, so this is from the work that I mentioned, Whitaker, and so this is the work that considered a single length scale for the clusters. The idea in that work was that if I look at the volume fraction of clusters, it lies, and by the way, these are exactly the same solid volume fractions and the same range of attractions that we are studying. In their system, the argument was that the overall volume fraction of clusters goes from 40% to about 60%. So if I look at this coarse-grained mesoscale view, I'm looking at a glassy dynamic. I'm in that range where I can imagine my clusters forming a glassy system. In our system, because we have a polydispersed nature, the volume fraction goes from about 70% to 90%. So it's more of a soft, glassy, squishy cluster picture rather than a glassy one, because we have very, very different length scales. The other thing that you can notice is that when I looked at individual particles contact distribution, there was not a huge difference as I went from weak to strong. But now I can identify how many cluster-cluster connections there are. So I'm looking at the mesoscale structures, not the individual components. And I can tell this cluster is connected to this, right? So that's what you're seeing here. And now you're seeing a very clear shift. As I go to stronger gels, not only, well, maybe as a result of that, my clusters are being more elongated and they're making more contacts with other clusters. So my mesoscale picture is one that is much more interconnected for the stronger gels. But if I look at the individual particles, I don't see that. These are the contact number for the clusters, not for the individual particles.
Very similar number.
The numbers are similar at the end, right? But the distribution is broader, right? So you have
These are large clusters, right?
yes, yes. So these are larger
These
clusters.
are not that they have the same number.
These are
Contacts as a
polydispersed.
particle.
Say again.
This is a single particle contact.
This one.
Yeah.
This one on the left.
And the other one.
This
the
one is
contact.
cluster.
Okay.
And you're counting how many clusters
Yeah,
you're
yeah.
connecting,
How
not
many
how
clusters?
many
Okay,
individual
very good.
contacts there is.
Cool.
Right? That is much bigger.
Yeah, okay. How many clusters?
Yeah.
Not how many.
So in the next step, what we did was, okay, so this is what we've done so far. From the simulation to a list of just nodes and edges that connect them to these clusters. And now we have these mesoscale objects. And in the next step, what Max did was basically just using a mass spring model to see what's the G prime for each of these basically mesoscale networks. And so what you're seeing here is exactly that. So these are the experiments, the crosses, and then the circles of what you get from a mass spring calculation for the G prime of these mesoscale structures. Suzanne.
G primed at what frequency do you mean G prime?
So this was, Max might remember that, but I don't, honestly. So these are all, these are, I think, yeah, so
So this is really whether it's solid at zero frequency. Okay.
basically zero free. Yeah. So the only information that, yes, come on.
So now the cluster is a rigid body. It has
At this point,
doesn't contribute to.
well, it's basically a mass at this point, right? There is a single node representing what the cluster is.
The assumption it doesn't.
It doesn't rearrange, it doesn't break up, none of that. Yeah.
Spring between the
And then the spring comes exactly from knowing just how many individual particle-particle connections connect to clusters. So if there are two, so there is, I know exactly what is the attraction energy between individual components. And if there are two nodes that are connecting them, I just multiply that by 2. If there are 3, I multiply that by 3. That's it.
not just necessarily the number of clusters. That
No. So that's the only information that's carried over. Yes?
So this is now literally just a central spring model in 3D.
Yes.
So it has some coordination number Z.
Yes.
So what would that Z look, average Z look like as a function of U? What's Z, but what's the average coordination number of this network as a function of U over K2?
Oh, so the average coordination number for the clusters, you mean? And
Well, in your
for this network would be the average that you get from this.
Looks like that's slightly below 6. Does that make sense?
So,
because it just looks as though it's just on the hairy edge of Maxwell.
good point.
Slightly
So when-
below even for
Yes,
the.
Yeah, so good point. When we go from individual components to clusters, and only if we have 2 or more individual components connecting clusters, we add a bending rigidity coming from that, and that's how you get the rigidity.
So that's why it's solid.
Yes,
Empty.
yes, absolutely. Otherwise, you wouldn't have bent.
Sorry, what was that again? If you have. when
So
you
if you have 2 clusters that are connected through more than one point, so the cluster-cluster connection represents more than one connection at the individual particle level, you add a bending rigidity there. Because supposedly there is a bonding rigidity now, because if you want to break it, it's not just in one direction.
But it's added as a bending resistance, or is it added as an extra spring?
No, it's added as a bending resistance.
That's another parameter which
So this
doesn't
is,
relate to you and.
we used, I believe for all of these, we didn't scale the bending spring constant for as we go from weak to strong. That we used the same bending rigidity for all of these clusters.
But it's a parameter which is needed to get a hard number for a G.
Yes,
So what is it?
it's, I want to make sure that I don't give you a wrong answer, but I think what we did was so it's, if I have 2 clusters connected to one, and each of those have more than one connection. What I do is, for that spring constant, I just get an average of what is this spring constant and this spring constant, and get a bending K that is used for all of these cases. Max, is that the same that you as you remember for this?
Right.
That's what I think we did.
The modulus of your springs, not depending, just the spring modulus, what is that varying too? Or is that...
It doesn't vary as we are, well, it's a product of what you have between individual components. It comes from that, right? So basically, it's the same scaling that you would have for the same like Cauchy-Born description, where you have U over KT, and that gives you a rigidity for individual connections.
The bend modulus doesn't even have the same units as the spring constant. So there's additional lengths which come in. So what is it? Is it the actual length between the two bonds that are?
Yes.
So then why isn't it more like just an extra spring? I don't get it. I don't know. Maybe that's a offline discussion.
We can talk about details of that.
Yeah.
I promise. So let me just move forward here and tell you what's coming next. So the main question I asked was, where do these gels yield from, right? So okay, this is again some reference to Emmanuel's old work and this idea that that when you put these gels under shear, what happens is you localize the stresses in certain points, and up to a point where now you break that bond, and the gel can relax in that particular location, just similar to a rubber snapping, right? So the overall chain, the force chain can relax. And the idea is like it accumulates until basically cannot hold it anymore. So there is this work by Karen Daniels' group on granular packing, which inspired what we did next. The idea was there was a geodesic edge between the centrality at of any given packing can be a descriptor of where the force, where the highest forces within the system. Meaning, if I visualize forces, and then I will explain what edge betweenness centrality is in a second, and I calculate this component edge betweenness centrality or geodesic edge betweenness centrality, there is a very direct correlation between the highest forces and the highest edge betweenness centralities. How do you calculate this? There is a very clear description, which is, imagine again, a single network, and you can get any 2 points within the network, I and J, right? And find the shortest path between them, between I and J. And list all the walks, all the individual edges that you have to cross from I to J. You list that. Now you get another I and J, and you do this iteratively for the entire combinations possible within a network. And the edge that shows up most frequently has to have the highest betweenness centrality, or is most central to connectivity within the network. Because any 2 points you take, you kind of have to cross through that edge. That's the idea. So that's, again, an easy calculation, iterative, mathematically. You just find all the shortest paths between any I and J combination, and you list them. The highest is the highest edge betweenness centrality. What we thought was that because these are known to, at least for granular packings, be very good predictors of where the stresses are highest, that could be similar for colloidal gels and being predictors of where stresses or strains are likely to be localized. So if I'm taking this theory that a stress localization ends up, giving rise to these microplastic events, I have to find where those are most likely. And that's what exactly we did. So we did basically the same process. And this network that you're seeing here is color-coded based on the value of high centrality to low centrality. So the warmer colors are just higher centrality values. So these are quiescent gels, right? So this is basically just saying which bonds are more central to connectivity of this network. Now, what we did next was we put these gels, so this particular structure, underflow at different Mason number. Yes.
You can look at the stresses in your simulation. Do they correlate with the?
You can look at the stresses under the formation, right? That's what you're referring to. For a snapshot, for a static picture.
That's what Karen did. She can measure forces. You can measure forces in your simulations.
Sure.
And do they correlate with this?
Oh, yes, absolutely, yes. No, what I meant was this value. The good thing about this is I can calculate that without knowing anything about the stresses. It's just topological.
Understood. I'm just asking if it correlates with the high stresses.
They do correlate, yes. So what I do is I put this gel under the formation at different rates. So this Mason number is just a pickle of depletion if you want. So attract basically shear forces to the attractive forces. And I'm looking at the overall number of connections as a function of a strain. And the point about this is that at this point of 0.1 a strain unit, it's already yielded. And the reason you don't see much of a change in the overall number of bonds is that there are some that are formed and there are some that are broken. But I know for a fact that at that point, the gel is yielded, it is flowing, and whatever happened within, whatever is responsible for yielding has to have already happened. So what I'm doing is this. I know exactly which bonds will be broken by this point, right? And I tag them. I run the simulations, and I know exactly which bonds are going to be broken by that time. Those should be the ones that are responsible for yielding. And those are the ones I'm showing here for two different Mason numbers. So all the blue ones are broken after a 0.1 a strain unit. So these are still the same picture because this is the quiescent gel. But after I put the formation on it, these blue ones will be broken, and these red ones are the high edge betweenness centrality ones. So what I'm going to do now is do a simple calculation of what are the fractions of each betweenness centrality value that is broken. And it turns out at the beginning I have a distribution of edge betweenness centralities. I have high ones and I have low ones. And after this 0.1 strain unit at different rates, what turns out is that it's always more likely to break the ones that are higher in their edge betweenness centrality. So this EBC value is a very good predictor of what will give rise to yielding. Because after 0.1 of strain, those are the ones that are broken. And if you look at this, the interesting thing is only almost half of those are broken. Why? Because if I break one, the other one will relax, and I don't have to break the other one. And again, these are calculated at the quiescent condition, so it's not a dynamic calculation at each point. So I broke the bond next to me, and I don't have to break. I can just stay intact, but the gel has already yielded. So you need sort of like half of those to break for the entire structure to yield. So the interesting thing is that this is universal for, so this was one volume fraction and one condition. You can do this for different volume fractions, 10%, 20%, 40%. You can change the attraction range, sure, and attraction strength, and for all of them, you will get the same thing. That it's always the highest edge betweenness centrality values within the network that will be broken when the gel has yielded. So, because I saw this mechanical tuning of gels in the previous talk, let me just bring this. And so George Pedekis has done work on this topic as well. This idea that mechanically shearing the system in the in pre-shear step can tune the G prime for the gels, and they have their own theories for it. But one question I had was, and this is very, very new, I just asked my postdoc to run these simulations, and he sent me the result over the weekend. The idea was, okay, now I'm doing a small amplitude oscillatory shear on the same structure. What happens to the EBC values? So if I look at the overall structure, these are the this is just at one amplitude of 0.05, relatively small, and these are all in DPD units, but at different frequencies, I don't see much of a change. But then the important thing is I only care about the high edge betweenness centrality values. So the tail of this, which is this one. And it turns out when you do the lower frequency, which is what George saw in his work, you slowly make the distribution towards smaller values of high edge betweenness centrality. What does that mean? You've made your network more uniform. You've made bonds almost as if they're now equally important to the centrality. So if I break one, I haven't really yielded, right? I have more to load the bear, to bear the load. So, and what you can see is that this is, if you look at the number of cycles, and when you do this over time, as you do more and more cycles, you make this more and more uniform. So in a sense, this is connected to what Jim was explaining. So it seems like really this EBC value is a good predictor of not only how the gel yields, but how you can fortify it. And what can you prescribe in pre-shear or any other protocols to fortify these high EBC values so that you end up with a more resilient gel. So I know I'm out of time. I'll just stop here. I'll try to answer any question you may have.